Right now, at this very moment, two enormous galaxies are drifting toward each other across the dark. One of them is the Milky Way, the galaxy you live in, a vast spiral of several 100 billion stars. The other is Andromeda, our nearest large neighbor, a slightly bigger spiral about 2.5 million light-years away. They are approaching each other at roughly 110 kilometers per second, about 250,000 miles per hour. That sounds fast, but the distance between them is so enormous that the collision will not happen for another 4.5 billion years. When it does happen, the result will be one of the most spectacular events in the history of these two galaxies. Stars will be flung across millions of light-years of space in great sweeping tidal tails. Enormous clouds of gas will compress and ignite, forming millions of new stars in brilliant bursts of light. Two supermassive black holes, each millions of times the mass of our Sun, will spiral toward each other and eventually merge. And yet, surprisingly, almost no individual stars will actually collide with each other. The spaces between stars are so vast that even when two galaxies pass through each other, their stars slide past like two swarms of fireflies in a dark field. Tonight, we are going to follow this story from beginning to end, calmly and in detail. We will start billions of years before the collision, when the first signs of the approach become measurable. We will watch the galaxies draw closer, feel the first gravitational tugs, and follow the tidal forces as they reshape both galaxies. We will see what happens during the chaotic middle stages, when shapes are destroyed and stars are scattered. We will witness the starburst, the final merger, and the birth of a new galaxy that astronomers have already named Milkromeda. The science behind all of this is well established, grounded in decades of observation, simulation, and mathematical analysis. So settle in, let your breathing slow, and let the story of two colliding galaxies carry you gently through the night. This is a story written in gravity, told across billions of years, and you already live inside it. Let us begin with what a galaxy actually is, and why these enormous structures behave the way they do. A galaxy is a gravitationally bound collection of stars, gas, dust, and dark matter, all orbiting a common center. The word galaxy comes from the Greek word galaxias, meaning milky, a reference to the pale band of light across our night sky. Galaxies come in several shapes. Spiral galaxies have beautiful curving arms of stars and gas winding outward from a central bulge. Elliptical galaxies are smoother and rounder, like luminous clouds of stars with no spiral structure at all. Irregular galaxies have chaotic shapes, often the result of gravitational interactions with other galaxies. Most large galaxies contain between 100 billion and a trillion stars, though the number varies enormously. But stars are only a small fraction of a galaxy's total mass. The majority of the mass is invisible. This invisible mass is called dark matter, and it forms an enormous spherical halo surrounding the visible galaxy. Dark matter does not emit or absorb light, but its gravitational influence shapes the rotation of galaxies and the motion of galaxy clusters. Fritz Zwicky first proposed the existence of dark matter in 1933 after studying the Coma galaxy cluster. He found that the galaxies in the cluster were moving too fast to be held together by the visible mass alone. Something unseen, something massive and dark had to be providing the extra gravitational pull. Vera Rubin and Kent Ford confirmed this in the 1970s by measuring the rotation curves of spiral galaxies. They found that stars far from the center of galaxies orbit just as fast as stars near the center. This flat rotation curve could only be explained if an enormous halo of invisible mass surrounded each galaxy. Today, we estimate that dark matter makes up about 85% of all the matter in the universe. In a typical spiral galaxy, the dark matter halo extends far beyond the visible stars, sometimes 10 times further. At the very center of most large galaxies sits a supermassive black hole, millions or billions of times the mass of our Sun. The black hole is tiny compared to the galaxy, but its gravitational influence shapes the inner regions profoundly. Between the stars lie vast clouds of gas and dust called the interstellar medium. These clouds are the raw material for new stars. When they are compressed by gravity or shock waves, they collapse and ignite. Star formation is an ongoing process in spiral galaxies. New stars are born along the spiral arms where gas is densest. The spiral arms themselves are not fixed structures, they are density waves moving through the disk like ripples across water. Stars drift in and out of the spiral arms as they orbit the galactic center. A galaxy is not a static thing, it is a living, evolving system, constantly changing over hundreds of millions of years. Galaxies grow by merging with other galaxies. This has happened many times throughout cosmic history. The Milky Way itself has absorbed several smaller galaxies over the past 12 billion years. Traces of these ancient mergers can still be found in streams of stars that loop around our galaxy in long, thin arcs. Galaxy mergers are one of the fundamental processes that shape the universe we see today. Understanding what happens when galaxies collide is central to understanding how the cosmos has evolved over billions of years. The Milky Way is a baad spiral galaxy, roughly 100,000 light-years across and about 1,000 light-years thick in the disk. It contains somewhere between 100 billion and 400 billion stars, along with enormous quantities of gas and dust. At its center lies a supermassive black hole called Sagittarius A star, with a mass of about 4 million suns. Sagittarius A star was imaged directly by the Event Horizon Telescope in 2022, confirming decades of indirect evidence. Our Sun sits about 26,000 light-years from the center, roughly 2/3 of the way out along one of the spiral arms. We orbit the galactic center once every 225 to 250 million years, a period sometimes called a cosmic year. The Milky Way has at least two major spiral arms, the Scutum Centaurus arm and the Perseus arm, along with several smaller ones. We live in a smaller spur called the Orion arm, or the local spur, between two of the major arms. The central bulge of the Milky Way is elongated into a bar shape, as seen in many other barred spiral galaxies. The bar rotates with its own pattern speed, separate from the rotation of the stars in the disk. Surrounding the visible disk is the galactic halo, a roughly spherical region containing old stars, globular clusters, and dark matter. Globular clusters are dense, ancient balls of stars, some containing hundreds of thousands of stars packed into a region only a few dozen light-years across. The Milky Way has about 150 known globular clusters, most of which are older than 10 billion years. The dark matter halo of the Milky Way is estimated to extend out to about 300,000 light-years from the center. The total mass of the Milky Way, including dark matter, is estimated at about 1.5 trillion solar masses. Only about 5% of that mass is in the form of stars. The rest is gas, dust, and dark matter. The Milky Way has a dozen or more small satellite galaxies orbiting around it. The two largest are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere. Several of these satellite galaxies are currently being stretched apart by the Milky Way's tidal forces. The Sagittarius Dwarf Elliptical Galaxy, discovered in 1994, is in the process of being absorbed right now. Its stars are being pulled into long streams that wrap around the Milky Way like ribbons. These ongoing mergers show that galaxy interactions are not rare events. They are happening all around us. The Milky Way is a dynamic, living galaxy shaped by billions of years of growth and merger. But the biggest merger in its future is still ahead. Andromeda is coming. And when Andromeda arrives, the Milky Way as we know it will be transformed beyond recognition. The Andromeda Galaxy, also known as Messier 31 or M31, is the nearest large galaxy to the Milky Way. It is a spiral galaxy, slightly larger than the Milky Way, with an estimated 1 trillion stars. Andromeda lies about 2.5 million light-years away, in the direction of the constellation Andromeda. On a clear, dark night, far from city lights, you can see it with the naked eye as a faint, elongated smudge. It is the most distant object visible to the unaided human eye, a pale glow that has travelled 2.5 million years to reach you. The Persian astronomer Abd al-Rahman al-Sufi described Andromeda as a small cloud in his Book of Fixed Stars in 964 AD. For centuries it was thought to be a nebula within our own galaxy, a cloud of gas rather than a separate island universe. In 1924, Edwin Hubble used Cepheid variable stars in Andromeda to measure its distance. He showed that Andromeda was far outside the Milky Way, proving that the universe contained other galaxies. This discovery transformed astronomy and expanded our understanding of the cosmos by a factor of millions. Andromeda has a supermassive black hole at its center, estimated at about 100 to 230 million solar masses. That is roughly 25 to 60 times more massive than Sagittarius A star at the center of the Milky Way. Andromeda has two small companion galaxies of its own, M32 and Min10, both visible in amateur telescopes. Min32 is a compact elliptical galaxy that appears to have had its outer stars stripped away by Andromeda's gravity. Andromeda's disk is tilted about 77 degrees to our line of sight, which is why it appears elongated rather than circular. Deep images reveal that Andromeda has a large, faint stellar halo extending far beyond its visible disk. This halo contains the remnants of many smaller galaxies that Andromeda has consumed over billions of years. Studies of these remnants suggest that Andromeda has undergone at least one major merger in its past, about 2 billion years ago. That ancient merger may have shaped the structure of Andromeda's disk and triggered a burst of star formation. Andromeda is still forming stars today, though at a lower rate than the Milky Way. Its spiral arms contain lanes of dark dust and regions of glowing gas when new stars are being born. The total mass of Andromeda, including its dark matter halo, is estimated at about 1.2 trillion solar masses. Some recent studies suggest the Milky Way and Andromeda are actually quite similar in mass, despite Andromeda appearing slightly larger. The two galaxies are gravitationally bound to each other. Their mutual attraction has been drawing them together for billions of years. The question is not whether they will collide, but exactly when and what the collision will look like. The story of how we discovered that Andromeda is approaching begins with the measurement of light. In 1912, the American astronomer Vesto Slipher measured the spectrum of light from Andromeda at the Lowell Observatory in Arizona. He found that the spectral lines of Andromeda were shifted toward the blue end of the spectrum. A blue shift means the source of light is moving toward the observer, just as the pitch of a siren rises as it approaches. This was the Doppler effect applied to light. Andromeda's light was compressed because the galaxy was moving toward us. Slipher measured Andromeda's radial velocity at about 300 kilometers per second toward the Sun. This was one of the first measurements of the motion of an object outside our own galaxy. Most other galaxies that Slipher measured were receding from us, showing redshifts. Andromeda was one of the rare exceptions. But knowing Andromeda's radial velocity, how fast it was approaching, was not enough. To predict whether the two galaxies would actually collide required knowing the tangential velocity as well. The tangential velocity is the sideways motion across the sky, and it is much harder to measure for distant objects. For nearly a century after Slipher's measurement, the tangential velocity of Andromeda remained unknown. Astronomers could tell Andromeda was approaching, but they could not tell whether it would pass by or hit us directly. The breakthrough came from the Hubble Space Telescope in 2012 in a study led by Roland van der Merel at the Space Telescope Science Institute. Van der Merel and his team measured the tiny sideways motion of stars in Andromeda by comparing Hubble images taken years apart. The motion was incredibly small, about 100th the apparent diameter of the full moon per century. But it was enough to determine that Andromeda's path is nearly head-on toward the Milky Way. The collision is essentially unavoidable. The two galaxies will begin their first close encounter in roughly 4 to 5 billion years. In 2019, the European Space Agency's Gaia satellite provided even more precise measurements. Gaia measured the proper motions of stars in Andromeda and its satellite galaxies with unprecedented accuracy. The Gaia data confirmed van der Merel's results and slightly refined the collision timeline. According to the latest estimates, the first close passage will occur in about 4.5 billion years. The final merger will be complete roughly 6 billion years from now. These numbers carry some uncertainty, perhaps 500 million years in either direction. But the overall picture is clear. Our galaxy and Andromeda are on a collision course that has been set for billions of years. The Triangulum galaxy, M33, the third largest member of our local group, may also be involved in the merger. Simulations suggest M33 could be absorbed earlier, or it could orbit the merged galaxy for billions of years before falling in. The local group, our small neighborhood of about 80 galaxies, will eventually be dominated by a single giant elliptical galaxy. This is the natural fate of galaxy groups throughout the universe. Gravity pulls everything together. The approach of Andromeda is not something to fear. It is simply the universe doing what it has always done. When two galaxies collide, the word collision can be misleading. It is not like two solid objects crashing into each other. Stars within galaxies are separated by enormous distances. The average distance between stars in the Milky Way is about 4 light-years. 4 light-years is about 38 trillion kilometers. That is an almost incomprehensible amount of empty space. If you shrank the Sun down to the size of a grain of sand, the nearest star would be another grain of sand about 6 kilometers away. When two galaxies pass through each other, their stars are so widely spaced that direct collisions between individual stars are extraordinarily rare. The probability of any two stars colliding during a galaxy merger is estimated to be less than 1 in a billion. So when we say galaxies collide, what actually happens is that their gravitational fields interact. The gravity of one galaxy pulls on the stars and gas of the other, stretching, distorting, and rearranging them. This gravitational interaction produces some of the most beautiful structures in the universe. Long tidal tails of stars are flung outward from the interacting galaxies, stretching across hundreds of thousands of light-years. Ridges of stars and gas can form between the two galaxies as material is pulled from one toward the other. The gas, unlike the stars, does collide. Clouds of hydrogen and other elements smash into each other at high speeds. These gas collisions compress the material to high densities, triggering intense bursts of star formation. A galaxy merger can increase the rate of star formation by a factor of 10 or more compared to an isolated galaxy. These starburst events produce millions of new stars in a relatively short period, astronomically speaking. The most massive new stars burn through their fuel quickly and explode as supernovae within a few million years. These supernovae inject energy and heavy elements back into the surrounding gas, enriching it for future generations of stars. Meanwhile, the gravitational interaction drives gas toward the centers of both galaxies. This infalling gas can feed the supermassive black holes at each galaxy's center, causing them to brighten dramatically. When gas falls onto a supermassive black hole, it heats up to millions of degrees and radiates intensely across the electromagnetic spectrum. An active galactic nucleus powered by a galaxy merger can outshine the entire host galaxy by a factor of 100 or more. Some of the brightest objects in the universe, called quasars, are thought to be powered by mergers feeding supermassive black holes. The process of merging is not quick. It takes hundreds of millions to billions of years from first contact to final coalescence. The two galaxies typically pass through each other once, separate, slow down, fall back together, and pass through again. Each pass dissipates orbital energy through a process called dynamical friction, described mathematically by Subramanian Chandrasekhar. Dynamical friction occurs because the gravity of a moving massive object attracts nearby matter, creating a wake behind it. That gravitational wake pulls back on the moving object, slowing it down, like dragging through a cosmic treacle. With each pass, the galaxies lose energy and come closer together on the next orbit. After several passes spanning billions of years, the two galaxies finally merge into a single, larger galaxy. The final product of a major merger between two spiral galaxies is typically an elliptical galaxy, smooth and rounded, with no spiral arms. The ordered rotation of the original spiral disks is disrupted and replaced by random stellar orbits. The result is a galaxy where stars move in all directions, like bees in a hive, rather than orbiting in a flat plane. This transformation from spiral to elliptical is one of the most fundamental changes in galaxy evolution. Many of the giant elliptical galaxies we observe today are believed to be the products of ancient mergers. The universe is full of merger remnants, beautiful in their own way, carrying the memory of their violent origins. The most visually striking features of galaxy mergers are the tidal tails, long streamers of stars and gas flung outward during the interaction. Tidal forces are the stretching forces that arise because gravity is stronger on the near side of an object than on the far side. The same tidal forces that cause ocean tides on Earth operate on the scale of entire galaxies. When two galaxies approach each other, the near side of each galaxy is pulled more strongly than the far side. This differential pull stretches each galaxy, drawing material outward in two opposite directions. The result is two long curving tails of stars and gas that can extend for hundreds of thousands of light years. These tidal tails are among the most beautiful structures in the observable universe. The physics of tidal tails was first explained in a landmark paper by Allah and Dusre, published in 1972 in the Astrophysical Journal. The Dusre brothers used early computer simulations to model the gravitational interaction between two disk galaxies. Their simulations were remarkably simple by modern standards, using only a few hundred particles to represent each galaxy. Yet the results were startlingly realistic. The simulations produced long tidal tails, bridges, and distorted shapes that match real observations. Dusre showed that many of the peculiar galaxies catalogued by Halton could be explained as interacting pairs. They proposed what became known as the Dusre sequence, a series of snapshots showing the stages of a galaxy merger. The sequence begins with two separate galaxies and ends with a single merged remnant, an elliptical galaxy. The Dusre brothers' 1972 paper is one of the most cited papers in extragalactic astronomy and remains influential today. The geometry of the encounter determines the shape of the tidal tails. A direct head-on collision produces symmetric tails. An angled encounter produces asymmetric, more complex shapes. The spin of each galaxy relative to the orbit also matters. Prograde encounters, where the spin aligns with the orbit, produce longer tails. Retrograde encounters, where the spin opposes the orbit, produce shorter and less prominent tails. The dark matter halo plays a crucial role. It provides the deep gravitational well that determines how far tidal material can escape. Stars that are flung into tidal tails do not necessarily escape the system entirely. Many eventually fall back into the merged galaxy over hundreds of millions of years. Some may form small dwarf galaxies within the tidal tails, called tidal dwarf galaxies. These tidal dwarfs are born from the debris of the interaction, a new generation of galaxies forged by the collision. Within the tidal tails, pockets of gas can compress and form new stars, creating blue knots of star formation along the streamers. These star-forming regions light up the tidal tails like beads on a string. The tidal tails eventually fade as the stars spread out and the gas disperses. But for tens of millions of years, they serve as dramatic markers of the gravitational forces at work. Tidal tails are visible evidence that gravity can reshape entire galaxies, rearranging hundreds of billions of stars. They are among the clearest and most beautiful confirmations of Newtonian and relativistic gravity operating on the largest scales. The universe provides us with many examples of galaxy mergers in progress, frozen at different stages for us to study. The most famous is the antennae galaxies NGC 438 and NGC 438 and NGC 439, located about 45 million light-years away in the constellation Corvus. The antennae are named for the two long tidal tails that extend outward from the merging pair, resembling the antennae of an insect. Hubble's Space Telescope images of the antennae reveal thousands of brilliant star clusters forming in the collision region. The star formation rate in the antennae is many times higher than in either galaxy before the merger began. The two galaxies began interacting about 600 million years ago and are now in the process of merging into a single galaxy. X-ray observations from the Chandra telescope show hot gas heated to millions of degrees by the collision. The antennae galaxies give us a preview of what the Milky Way and Andromeda will look like in about 5 billion years. Another famous pair is the mice galaxies, NGC 4666, named for their two long, thin tidal tails that resemble mouse tails. The mice are about 290 million light-years away and are in an early stage of their merger. They have passed through each other once and are falling back together for the second time. The long, straight tidal tails of the mice are textbook examples of the features predicted by rahe and rahe. NGC 6200 is a more advanced merger, about 400 million light-years away, where two galaxies are nearly fully combined. NGC 6200 is remarkable because it contains two supermassive black holes separated by only about 3,000 light-years. These two black holes are spiraling toward each other and will eventually merge. The Cartwheel Galaxy, about 500 million light-years away, shows what happens in a direct head-on collision. A smaller galaxy punched through the center of a larger spiral, creating an expanding ring of star formation like a ripple in a pond. The ring is about 150,000 light-years in diameter and contains billions of new stars. ARP 222 is an ultra-luminous infrared galaxy about 250 million light-years away, the product of a recent major merger. It radiates most of its energy in the infrared because thick dust produced by the merger absorbs visible light and re-emits it at longer wavelengths. The merger in ARP 220 has triggered an enormous starburst, forming new stars at a rate hundreds of times greater than the Milky Way. The Whirlpool Galaxy M51 and its companion NGC 5195 are in the early stages of interaction. The smaller companion is pulling tidal material from the larger spiral, creating a bridge between them. N51 was one of the first galaxies recognized to have spiral structure by Lord Rosse in 1845 using his large telescope in Ireland. Each of these systems tells us something different about the merger process. Early encounters produced long tails and bridges. Advanced mergers show double nuclei and intense starbursts. Late-stage mergers transition into smooth elliptical shapes as the orbital energy dissipates. By studying galaxies at every stage, we can reconstruct the entire timeline of a collision. It is like having photographs of a caterpillar, a chrysalis, and a butterfly, and understanding the full transformation. These observed mergers confirm the predictions of both analytic theory and computer simulations with striking fidelity. Now let us look ahead to what will happen when the Milky Way and Andromeda actually meet. For the next 4 billion years, the two galaxies will continue their slow approach, growing larger in each other's sky. From Earth, Andromeda will appear to grow over the eons. Today it subtends about 3 degrees on the sky, 6 times the diameter of the full moon. But its surface brightness is low, so it is barely visible to the naked eye despite its large angular size. As the galaxies draw closer, Andromeda will eventually span tens of degrees across the sky, a luminous presence impossible to ignore. About 4 billion years from now, the outer halos of dark matter will begin to overlap and interact. The dark matter halos extend far beyond the visible galaxies, so the gravitational interaction begins long before the stars approach. The first visible effects will be subtle distortions in the outer spiral arms of both galaxies. Stars in the outskirts will begin to deviate from their normal orbits, pulled gently by the approaching galaxy. About 4.5 billion years from now, the first close passage will occur. The two galaxies will rush past each other at a relative speed of several hundred kilometers per second. During this first pass, the tidal forces will dramatically reshape both galaxies. Long tidal tails will be drawn out from both the Milky Way and Andromeda. The spiral structure of both galaxies will be severely distorted, with arms stretched and twisted. Enormous quantities of gas will be compressed in the region between the two galactic centers. This compression will trigger the first major wave of new star formation. Bright blue star clusters would appear in the compressed gas, lighting up the space between the galaxies. From a hypothetical planet in either galaxy, the night sky would be transformed. Instead of a faint smudge, The other galaxy would fill half the sky with brilliant spiral arms and glowing gas clouds. The Sun, if it still exists at this point, will be about 9.5 billion years old, nearing the end of its main sequence life. Whether Earth is still habitable at this point depends on the Sun's evolution more than on the galaxy merger. The merger itself poses little direct danger to individual star systems. Stars are far too widely spaced to collide. But some stars will be gravitationally ejected from their home galaxy during the interaction. A small percentage of stars, perhaps a few percent, will be flung into intergalactic space, becoming rogue stars with no galaxy. Our own Sun has a small but non-zero chance of being among those ejected stars. Simulations by van der Marel and others suggest about a 12% chance that the Sun will be moved to the outer tidal tails, and about a 3% chance that it will be captured by Andromeda before the merger is complete. After the first pass, the two galaxies will separate again, their momentum carrying them apart. But dynamical friction will have stolen energy from their orbits, so they will not travel as far apart as before. They will slow, stop, and begin falling back together for the second encounter. After the first pass, the two galaxies enter a period of gravitational chaos that lasts hundreds of millions of years. The orderly spiral structure of both galaxies has been severely disrupted. Stars that were following neat circular orbits have been thrown onto wild, elongated paths. The tidal tails stretch outward, carrying stars and gas far from the main bodies of the galaxies. Some of this tidal material will rain back down on the merging system over the next billion years. The two galaxy cores, each still containing their supermassive black hole, begin their long gravitational dance. They orbit each other, drawing closer with each revolution as dynamical friction continues to drain their orbital energy. Chandrasekhar's formula for dynamical friction, published in 1943, provides the mathematical framework for understanding this process. As the massive cores move through the surrounding sea of stars and dark matter, they create gravitational wakes behind them. These wakes act like a drag force, steadily converting orbital energy into random motions of surrounding stars. The process is slow but relentless. Each orbit brings the two cores closer together. During this chaotic phase, the shapes of the merging galaxies become difficult to classify. They no longer look like spirals. They are irregular, asymmetric masses of stars and gas with tidal debris everywhere. Astronomers call this phase the train wreck stage, when the merger looks most violent and disordered. Stars are accelerated to high velocities during close encounters with the dense galactic cores. A process called violent relaxation, described by Donald Lyndon Bell in 1967, redistributes the energy of stars. In violent relaxation, the rapidly changing gravitational potential gives and takes energy from individual stars in a random way. This process eventually converts the ordered rotation of the original disks into the random motions of an elliptical galaxy. The gas in the system is also violently disturbed. Shockwaves propagate through the interstellar medium at thousands of kilometers per second. These shocks heat the gas to millions of degrees, causing it to emit X-rays visible to space telescopes like Chandra. At the same time, some of the shocked gas cools rapidly in fragments, creating new sites for star formation. The interplay between heating and cooling determines the ultimate fate of the gas in the merger. Some gas is consumed in starbursts, some is heated until it escapes the galaxy entirely. Some falls toward the center and feeds the supermassive black holes. The chaotic phase is also when large-scale magnetic fields in both galaxies become tangled and amplified. Turbulence in the gas stretches and folds the magnetic field lines, increasing the magnetic energy density. These amplified magnetic fields can influence subsequent star formation by providing support against gravitational collapse in some regions. The gravitational chaos is not destruction, it is transformation. From the disorder of the merger, a new, more stable structure will eventually emerge. The universe builds beauty from chaos, and galaxy mergers are among its grandest examples. One of the most dramatic consequences of a galaxy merger is the starburst, an explosive increase in the rate of star formation. In an isolated spiral galaxy like the Milky Way, New stars form at a rate of about 1 to 3 solar masses per year. During a major merger, that rate can increase to tens, hundreds, or even 1,000 solar masses per year. The starburst is triggered by the compression of gas. As the two galaxies interact, their gas clouds are pushed together. When gas is compressed beyond a critical density, it becomes gravitationally unstable and begins to collapse. The collapse fragments the gas into smaller and smaller clumps, each of which can form a new star or star cluster. The most intense starbursts occur in the nuclear regions, where gas is driven toward the galactic centers by gravitational torques. Bar structures that form during the interaction are particularly effective at funneling gas inward. The resulting nuclear starburst can produce so many stars that the center of the galaxy glows brilliantly in infrared light. Much of this light is absorbed by dust and re-emitted at infrared wavelengths, making merger starbursts extremely luminous in the infrared. Luminous infrared galaxies, or LIRGs, and ultraluminous infrared galaxies, or ULIRGs, are almost always associated with mergers. The most massive stars formed in the starburst have lifetimes of only a few million years. They burn brilliantly, ionizing the surrounding gas with their ultraviolet radiation, and then explode as supernovae. A major starburst can produce thousands of supernovae over a period of a few million years. These supernovae create a superwind, a hot outflow of gas driven outward by the combined energy of many explosions. Superwinds can eject gas from the galaxy entirely, sending metal-enriched material into the intergalactic medium. This ejected gas carries heavy elements forged in the stars, seeding intergalactic space with the raw materials for future stars. The starburst does not last forever, it is self-limiting. The combination of gas consumption by star formation and gas ejection by supernovae and black hole feedback eventually exhausts the fuel supply. Once the gas is depleted, star formation drops dramatically and the galaxy enters a quieter phase. This transition from starburst to quiescence is sometimes called quenching. The merger remnant, now an elliptical galaxy, will have very little gas left and will form new stars only slowly, if at all. The starburst is the galaxy's last great act of creation before settling into a calmer existence. In the Milky Way Andromeda merger, the starburst will likely produce a brief but brilliant increase in the beauty of the night sky. From a planet in the merged galaxy, the sky would blaze with young hot blue stars and glowing pink nebulae. At the heart of the Milky Way Andromeda collision lies one of the most extraordinary events in all of physics. The supermassive black holes at the centers of both galaxies will eventually merge. Sagittarius A star, with its 4 million solar masses, will meet Andromeda's central black hole, which may be 50 to 100 times more massive. The merger of supermassive black holes is a process that occurs in 3 distinct stages. In the first stage, dynamical friction brings the two black holes from galaxy-scale separations down to about a parsec, roughly 3 light-years. This phase takes hundreds of millions of years as the black holes orbit within the merged stellar system. In the second stage, the black holes interact gravitationally with individual stars that pass nearby. Stars that come close to the binary black hole are flung outward at high speeds in a process called gravitational slingshot. Each ejected star carries away a tiny amount of the binary's orbital energy, causing the two black holes to spiral slightly closer. This stellar scattering phase can take a very long time, potentially billions of years, depending on how many stars are available. This slow phase is sometimes called the final parsec problem, because it was unclear whether the black holes could cross this last gap. Recent simulations suggest that the rotating, triaxial shape of the merger remnant feeds new stars into the loss cone efficiently. The loss cone is the region of orbital parameter space that brings stars close enough to the binary to interact. In the third and final stage, the two black holes are close enough that gravitational wave emission dominates. Gravitational waves carry energy away from the binary, causing the orbit to shrink rapidly in the final moments. The shrinking accelerates as the black holes draw closer, the waves grow stronger, and the orbit tightens faster. In the last few orbits, the two black holes spiral together at a significant fraction of the speed of light. The gravitational waves emitted during this final inspiral and merger are among the strongest signals in the universe. The supermassive black holes of this mass, the gravitational waves, have very low frequencies, too low for LIGO to detect. They fall in the frequency range of the planned LISA mission, the Laser Interferometer Space Antenna. LISA, planned for launch in the 2030s, will consist of 3 spacecraft separated by millions of kilometers, forming a giant triangle in space. LISA will be able to detect the merger of supermassive black holes across the entire observable universe. When the two black holes finally merge, the resulting single black hole rings down, emitting gravitational waves as it settles into a stable state. This ring down is described by the Kerr metric, the solution for a rotating black hole derived by Roy Kerr in 1963. The merged black hole will have a mass slightly less than the sum of the two original masses. The missing mass, typically a few percent, has been radiated away as gravitational wave energy. For the Milky Way Andromeda merger, this radiated energy is equivalent to millions of solar masses converted entirely to gravitational radiation. The gravitational wave energy released in a supermassive black hole merger exceeds the light output of every star in the observable universe combined briefly. Pulsar timing arrays, using millisecond pulsars as precise cosmic clocks, may detect the gravitational wave background from many such mergers across the cosmos. The merger of two supermassive black holes is the most energetic event in the universe after the Big Bang itself. After several billion years of gravitational interaction, the Milky Way and Andromeda will finally merge into a single galaxy. The process will not have a sharp ending. It is a gradual transition from two separate systems to one. Astronomers have given the future merged galaxy a name, Milkdromeda, a blend of Milky Way and Andromeda. Some researchers prefer the name Milkomeda, which has a slightly different ring to it. Regardless of name, the merged galaxy will be a giant elliptical galaxy, much larger than either of its two parent spirals. It will contain roughly 1 trillion stars, drawn from both the Milky Way and Andromeda. The spiral structure of both original galaxies will be completely gone, replaced by a smooth, rounded distribution of stars. The stars will orbit the center of the merged galaxy in random directions, creating a 3-dimensional ellipsoidal shape. The central supermassive black hole, the merged remnant of Sagittarius A star and Andromeda's SMBH, will dominate the core. Most of the gas will have been consumed in starbursts, heated to high temperatures, or ejected from the galaxy by supernovae and black hole feedback. Milkdromeda will be a red and dead galaxy, dominated by aging, reddish stars with very little ongoing star formation. This is the fate of most giant elliptical galaxies. They burn through their gas during the merger and then age quietly. The Triangulum galaxy, M33, may be incorporated as well, either before or after the main Milky Way Andromeda merger. Many of the smaller dwarf galaxies in the local group will also be absorbed over the following billions of years. Eventually, the entire local group will be a single giant galaxy surrounded by the vast emptiness of intergalactic space. As the universe continues to expand, the distances to other galaxy groups will grow ever larger. In the very distant future, trillions of years from now, Milkdromeda will be essentially alone in the observable universe. Other galaxies will have receded beyond the cosmic horizon, carried away by the accelerating expansion of space. The night sky from within Milkdromeda will eventually show nothing beyond the galaxy itself. No other galaxies, no cosmic web. Just the quiet glow of 1 trillion aging stars, slowly fading into the dark. But that is a story for the far, far future. For now, Milkdromeda is a promise, a beautiful ending written in gravity. The merger will transform both of the galaxies we know into something new, something neither one could have become alone. It is destruction and creation in a single, slow, gravitational embrace. And there is a quiet elegance in knowing that this future is already set in motion, determined by the physics we understand today. Milkdromeda is waiting for us, written in the equations of gravity, patient and inevitable. Dark matter plays a central role in galaxy mergers, even though it is completely invisible. The dark matter halos of two approaching galaxies are the first components to interact. Because the halos extend far beyond the visible galaxies, the gravitational interaction begins billions of years before the stars meet. Dark matter does not collide with itself the way gas does. It passes through the other halo almost freely. This is because dark matter interacts only through gravity and possibly the weak nuclear force, not through electromagnetism. When two dark matter halos overlap, they create a complex gravitational potential that reshapes the orbits of everything within them. Dynamical friction between the two halos is the primary mechanism that brings the galaxies together. Without dark matter, galaxy mergers would proceed very differently, much more slowly, or not at all in some cases. The dark matter provides the deep gravitational well that keeps the system bound during the violent phases of the merger. Stars and gas that are flung outward by tidal forces are often recaptured because the dark matter halo is so massive. Simulations show that removing dark matter from the model produces merger remnants with very different properties. The shapes, sizes, and velocity distributions of observed merger remnants match the dark matter simulations, not the dark matter-free ones. The bullet cluster, observed in 2006, provided some of the most compelling direct evidence for dark matter in a merger. In the bullet cluster, two galaxy clusters collided, and the hot gas was slowed by electromagnetic interactions while the dark matter passed through. Gravitational lensing revealed that most of the mass had passed through, separated from the visible gas. This separation between where the mass is and where the gas is can only be explained if most of the mass is dark matter. The bullet cluster observation, led by Douglas Clough and colleagues, was published in the Astrophysical journal, Letters in 2006. It provided what many consider the most direct proof of dark matter's existence. In the Milky Way Andromeda merger, the dark matter halos will merge first, creating a single large halo. The visible galaxies will then settle within this combined dark matter halo, guided by its gravitational potential. The final elliptical galaxy, Andromeda, will be embedded in a dark matter halo roughly twice as massive as either original halo. Understanding the role of dark matter in mergers is essential for understanding how galaxies evolve. It is a humbling reminder that most of the matter shaping our galaxy's future is something we cannot see. Fritz Zwicky would be pleased. The dark matter he proposed in 1933 turns out to be the architect of galaxy evolution. The invisible shapes the visible, and gravity is the thread that connects them. Everything we know about the future of the Milky Way Andromeda collision comes from computer simulations. These are called n-body simulations because they track the gravitational interactions of n particles representing stars and dark matter. The first galaxy merger simulations, like those of Tumor in 1972, used only a few hundred particles. Today, the most advanced simulations use billions of particles and run on the world's most powerful supercomputers. The Illustris simulation and its successor, Illustris TNG, model the formation and evolution of thousands of galaxies in a cosmological volume. These simulations include not just gravity but also gas dynamics, star formation, supernova feedback, and black hole growth. The FIRE simulations, feedback in realistic environments, focus on individual galaxies with extremely high resolution. For the specific case of the Milky Way Andromeda merger, detailed simulations have been run by Van der Merel, Cox, and others. These simulations use the measured positions, velocities, and masses of both galaxies as starting conditions. They then evolved the system forward in time using Newton's law of gravity, computed for every pair of particles at each time step. The results consistently show a first passage in about 4.5 billion years, followed by several more encounters over the next 1 to 2 billion years. The final merger into an elliptical galaxy is complete roughly 6 to 7 billion years from now. Different initial conditions, slight variations in the tangential velocity or the mass ratio produce slightly different outcomes. But the overall story is robust. The merger will happen and the result will be an elliptical galaxy. Modern simulations can even predict the colors and surface brightness profiles of the merger remnant. They show that the remnant will be consistent with observed giant elliptical galaxies in the nearby universe. The simulations also make predictions about what the night sky will look like from within the merged galaxy at various stages. These predictions have been visualized by NASA and others, creating stunning animations of the future collision. N-body simulations are the telescopes with which we observe the future. They let us see events that no human will witness. They are one of the most powerful tools in modern astrophysics, turning equations into movies of the cosmos. One of the most captivating questions about the merger is what the night sky would look like from Earth during the collision. Today, Andromeda is a faint, elongated smudge in the constellation Andromeda, barely visible to the naked eye. It subtends about 3 degrees on the sky, but its surface brightness is very low. 2 billion years from now, Andromeda will be noticeably closer and brighter, spanning more of the sky. 3.5 billion years from now, it will dominate the evening sky, a great spiral presence covering tens of degrees. The spiral arms of Andromeda will be clearly visible, a vast pinwheel of stars and glowing gas clouds stretching from horizon to zenith. At 4.5 billion years, during the first close passage, the sky will be almost unrecognizable. Earth galaxies will be distorted, with tidal tails arcing across the sky and star-forming regions blazing with blue light. The Milky Way band itself will be warped and distorted, as our own galaxy's shape is changed by the interaction. New star clusters born in the starburst will appear as bright knots scattered across the sky. Some of these young clusters will be among the brightest objects visible, rivaling the brightest stars. During the chaotic phase, after the first passage, the sky may show streamers and bridges of stars connecting the two distorted galaxies. Pink emission nebulae, heated by newly formed massive stars, will blow in the sky like celestial flowers. As the two galaxies settle into their final merger, the diffuse glow of stars will surround the observer in all directions. Instead of the narrow band of the Milky Way, the sky will glow uniformly with a soft, warm light. The familiar constellations will be impossible to recognize. Every star pattern will have changed. The Sun itself, if it survives to this point, may be in a completely different part of the galaxy than where it started. NASA has produced visualizations of this future sky using data from N-body simulations. The images show a sky that transitions from the familiar narrow Milky Way band to a sky filled with galactic light from every direction. It would be beautiful beyond description, a sky ablaze with the light of 1 trillion stars merging into one. No human will see this sky, but the fact that we can predict it in detail using physics and computation is remarkable. The equations of gravity, written by Newton and refined by Einstein, allow us to peer billions of years into the future. We can describe the night sky of a world that does not yet exist, lit by stars that have not yet been born. There is something quietly astonishing about that. Physics gives us the future as well as the past. And in this case, the future is beautiful. We have followed the story of two galaxies from their current separation of 2.5 million light-years to their final union. Along the way, we have met tidal tails and starbursts, supermassive black holes and dark matter halos. We have seen how gravity, the gentlest of the fundamental forces, shapes the largest structures in the universe. The collision between the Milky Way and Andromeda is not a catastrophe, it is a transformation. Two spiral galaxies will become one elliptical galaxy, larger and more massive than either alone. The process has been happening throughout the universe for 13 billion years. It is how galaxies grow. The Tomb Red brothers showed us how tidal forces create beauty from gravitational interaction. The Hubble Space Telescope has shown us dozens of mergers in progress, frozen at every stage for us to study. Vandermarlel and the Gaia satellite confirmed that our merger is real, measured, and inevitable. Chandrasekhar gave us the mathematics of dynamical friction, the process that seals two galaxies' fate. Fritz Zwicky and Vera Rubin revealed the dark matter that makes it all possible. And N-body simulations let us watch the future unfold, frame by frame, on a computer screen. You live inside one half of this future collision. Every star you see tonight is part of the story. The faint smudge of Andromeda in your sky is a galaxy that is heading toward you right now at 110 kilometers every second. In 4.5 billion years, it will arrive, and when it does, the universe will make something new from what we know. There is no danger in this collision. Stars are too far apart to hit each other. If a planet like Earth exists in the merged galaxy, its inhabitants will see a sky more beautiful than anything we can imagine. A sky filled with 1 trillion stars, glowing nebulae, and the quiet aftermath of the greatest construction project gravity has ever undertaken. Let this thought settle gently into your mind as you rest. The universe is not static. It is always building, always merging, always creating. And you are part of it. Every atom in your body was forged in a star inside a galaxy, shaped by gravity. The galaxy you live in is on its way to becoming something new, and that is not an ending. It is a beginning. Rest now. Let the slow, patient gravity of the cosmos carry you gently into sleep. Andromeda is approaching. The stars are drifting, and the universe is quietly, beautifully building the future. Good night. Galaxies did not always exist. In the earliest moments of the universe, there were no stars, no galaxies, only a nearly uniform sea of hydrogen and helium. Tiny density fluctuations in that primordial gas, imprinted during the Big Bang, seeded the formation of all cosmic structure. Dark matter collapsed first, forming halos that pulled ordinary gas inward through gravity. Within these dark matter halos, the gas cooled, condensed, and began forming the first stars about 200 million years after the Big Bang. These first stars were enormous, hundreds of times the mass of our Sun, and burned through their fuel in just a few million years. When they exploded as supernovae, they enriched the surrounding gas with heavier elements like carbon, oxygen, and iron. The first galaxies were small and irregular, containing only millions of stars rather than billions. Over billions of years, these small proto-galaxies merged with each other, growing into larger and larger systems. This hierarchical merging is the fundamental process by which galaxies grow. Small galaxies merge to form large ones. The Milky Way itself was built from dozens of smaller galaxies that merged over cosmic time. Evidence of these ancient mergers is written in the ages and chemical compositions of stars throughout our galaxy. The oldest stars in the Milky Way's halo are relics of these early mergers, carrying the chemical fingerprints of their birth galaxies. Galaxy formation is not finished. Mergers continue to this day, reshaping galaxies across the cosmos. The Milky Way Andromeda collision is simply the next chapter in a story that began 13 billion years ago. Every galaxy is a story of mergers, written in starlight and shaped by the patient hand of gravity. Our understanding of galaxy mergers has been transformed by space telescopes and ground-based observatories. The Hubble Space Telescope, launched in 1990, has provided some of the most detailed images of merging galaxies ever captured. Hubble's resolution allows astronomers to see individual star clusters forming in the collision regions of distant merging galaxies. The James Webb Space Telescope, launched in 2021, observes in infrared wavelengths piercing through the dust that obscures much of the starburst activity. Webb has revealed previously hidden details of galaxy mergers, including buried starbursts and active galactic nuclei. The Chandra X-ray Observatory detects the hot gas produced when the interstellar media of two galaxies collide. X-ray observations reveal shocked gas heated to temperatures of millions of degrees, invisible at optical wavelengths. The Atacama Large Millimeter Array, ALMA, in Chile, observes the cold molecular gas that fuels star formation in mergers. ALMA can map the distribution and motion of gas clouds in merging galaxies with extraordinary precision. Ground-based optical telescopes like the Very Large Telescope and the Keck Observatory provide spectroscopic data. Spectroscopy reveals the velocities, temperatures, and chemical compositions of stars and gas in merging systems. Radio telescopes detect the neutral hydrogen gas that forms the raw material for star formation in galaxy interactions. Observations at every wavelength contribute a different piece of the puzzle. building a complete picture of what happens during a merger. The combination of all these instruments allows astronomers to study mergers from the first tidal interaction to the final relaxed remnant. Each new telescope generation reveals more detail, confirming and refining the theoretical models of galaxy evolution. The Milky Way and Andromeda are the two largest members of a small galaxy cluster called the Local Group. The Local Group contains about 80 known galaxies, most of them small dwarf galaxies. The third largest member is the Triangulum Galaxy, M33, a small spiral about 2.7 million light-years away. M33 may fall into Andromeda before the main merger, or it may orbit the combined system for billions of years. The Local Group spans about 10 million light-years across, a tiny corner of the observable universe. Beyond the Local Group lies the Virgo supercluster, a vast collection of galaxy groups and clusters. The Virgo supercluster is itself part of an even larger structure called Laniakea, identified in 2014. Laniakea contains about 100,000 galaxies spread across 500 million light-years. But the accelerating expansion of the universe means that most of these distant galaxies will recede from us over time. Only the gravitationally bound members of the Local Group will remain together in the far future. All the galaxies in the Local Group will eventually merge into a single giant galaxy over the next several hundred billion years. The Milky Way-Andromeda merger is just the first and largest step in that process. In the very distant future, the merged galaxy will be alone in an expanding, cooling universe. The stars will slowly age and fade. New stars will form ever more rarely as the gas supply dwindles. But that is a story for the far future. For now, the Local Group is alive with motion and interaction. There is something deeply calming about the timescales involved in galaxy mergers. The approach of Andromeda has been underway for billions of years. It will continue for billions more. On these scales, human civilization is a brief flash, a momentary awareness in the long gravitational dance of galaxies. Yet in that brief moment, we have understood the physics well enough to predict the future of our galaxy. Newton's law of gravity, published in 1687, describes the force that will drive this merger. Einstein's general relativity, published in 1915, refines that description for the most extreme conditions near the merging black holes. The same equations that describe an apple falling from a tree describe two galaxies falling toward each other. Gravity is the weakest of the fundamental forces, yet it is the one that shapes the largest structures in the universe. It is the architect of galaxies, the sculptor of clusters, and the engine of cosmic evolution. Every star you see tonight is held in its orbit by gravity. Every galaxy in the sky is shaped by gravity. And the collision that will transform our galaxy is driven by the same gentle force. There is no rush. Gravity is patient. It has all the time in the universe. Let that patience be yours tonight. Let the slow certainty of gravity carry you gently into rest. The galaxies will merge, the stars will rearrange, and something beautiful will emerge from the collision.